Swayam Prabha. Digital India. Educated India.
Meanwhile, if anyone has any questions on things we discussed so far, I can help and answer them.
I have a general question, but it might be unrelated.
Yeah, sure, go ahead.
I recently found out that even compiled languages like C have a runtime. I originally thought that like the compiler just generated code and it ran on the processor, but like, even C has
By
a runtime.
C runtime, you meant something called a CRT or something else?
Oh, I don't know. I just know that there's a runtime and it's supposed to, I think, set up the program for execution.
Correct. Actually, if I get to that, I do have that covered in my slide set. But to answer it briefly, so think of it this way. I'll ask you a question and you can probably think why it's needed. So you probably know that main function also takes some parameters, right? It takes the
Right.
arguments that were passed from the command line, and it has this int argc char star star argv. Who
Yes.
passes that to main, right? And how does that get passed? That's where the C runtime kind of comes into picture. So main is not the first thing that actually gets executed. There is something called as underscore start, which actually executes it, and underscore start, what it includes, forms what I would call a C runtime. I actually have a slide on that. Hopefully, if we get to that stage, I'll explain. Otherwise, I'll anyway share my entire slide, so hopefully you'll get info from that.
Sorry to interrupt. I had a follow-up question on this. So my understanding was that when we create a process, we fork a process out of the init, right?
Correct.
And basically what is happening is that init creates a child process and then it passes the control. And by passing the control, we mean that it pushes the arguments on top of its stack and then makes a function call. And that function happens to be the main of the child process.
It is slightly different than that. I would say at a preliminary level, what you said makes sense from understanding point of view, but there is some more details to it. Maybe I'll just go to that slide just for interest of time. If we get to that in a detail, that's still fine. Otherwise, some repetition. So essentially what happens is the entry point in ELF is always pointing to something called as underscore start. And process doesn't actually start executing from when. It starts executing from underscore start. So whenever you do fork or anything, it actually starts executing underscore start. Okay. And what underscore start logically is doing, right? This is more like pseudocode. I'm not saying this is the exact code which it has. It does something called as libc init, where it is setting up the start code. Then it has some init, at, exit, and so on. And then it calls main. And then it would do the exit. The actual execution happens something like this, which is more complicated. But to give an example of why this init and stuff like this is needed, is imagine you have something like, let's say I write a code something like this. Can you see my screen where I have editor open?
Yeah.
Yes.
Okay. Let's say I have something like this. Change it to some. Did you realize what just happened in this? So essentially I have var, okay, which I have initialized with a function call. This function call executes, it returns some value. And all of this happens before main. Where was initialized before the main is supposed to start. How was it initialized if the main is the first thing that executes?
Oh, this is a functor, right? You just made a function pointer call and it did a jump. No, but okay,
It
how did
happened before
the
main.
print? Yeah.
Yeah, it happened before main. So you could see that printed hello in foo first. Let me also print something like hello in main here, just in case there is some confusion. You can see hello in foo happened before hello in main.
Yeah, thank you. That's a really good example.
Okay, so that's
Sure.
what CRT was doing.
Thank
And
you.
when CRT, so when this init happens, this is where it is actually initializing all these variables that were initialized at module scope. And if it has any dynamic code like function call, etc., it would actually do that. At exit will essentially set up any exit handlers that your code. So for example, in C, there are some system calls which allow you to overwrite at exit handler, which say that once the program exit, instead of directly exiting to operating system, please call my user defined function. So this would set up those kind of handlers, and then the actually main will get called. And before calling the main, obviously it would set up all those argc, argv parameters and so on. Okay, so the actual initialization looks more complicated like this, but I'll not go into that. Okay, I think we probably have others now, so we can start with linkers. Okay, any other questions on this topic before we begin with linkers? Okay, so what do linkers do, right? So we saw that we have main.c, foo.c, which got compiled to object files. Linker needs to somehow merge these two things together, right? So linker needs to somehow take main.o, foo.o, combine them together, right? It also needs to do symbol resolution, where it needs to say that, okay, extern int foo here is same as int foo, which was in foo.o, right? And this process, unfortunately, is not as trivial as it may sound. So we'll see some details of it. But it is essentially trying to establish which reference corresponds to which definition. Okay, and the reference and definition may be spanning across different object files. And it performs something called as relocation, which we will see in more details. But what it means is it kind of arranges symbols in a different way and update all the references. This is something similar to what I was saying earlier to one of the questions which was asked, that whether the jumps happen from one text section to other text section, where I said that linker will combine all the text sections. So we'll see what it does internally in that. Okay, so now we so far were seeing only the elf relocatable file view, right? Linker is essentially taking multiple elf relocatable objects and actually creating a executable elf object. Now, as I had mentioned at the very beginning when I started introducing elf, that elf is a format which is capable of representing both information. Okay, in some cases you might, I mean, if you're not using elf and if you're using some other formats, you might have a different kind of format on the relocatable side, and you may have a different kind of format on the executable side, which is what happens in Windows. So in Windows, the relocatable object files follow a different format, and the exe file which is produced follows a different format. But in elf, it's the same format, but with a different view, which enables the same thing to happen. So what linker is doing is essentially, it has every elf file will have all of this. It has elf header, various sections, and the other elf file will also have the same thing. So linker will combine these things together into segments. Okay, so all the text sections which are present in every header, every elf relocatable file. All of those will get merged together to form a text segment. Okay, all of the data sections that are present will form data segment and so on. Okay, so all the logical data which is of similar kind will get merged together to form a segment. Okay, and once this is done, linker will start resolving the symbols, because as you can see, so let's say someone was at offset 0 in this dot data. After merging, it cannot be at offset 0 because offset 0 might correspond to this data, right? So you have to somehow update the references. Okay, but we'll see that part later. First, we'll look at how the symbol resolution itself works. Okay, now remember what symbols are relevant for linker, right? I already mentioned this, that there are global symbols. Global here essentially means symbols that are defined in the object files and can be referenced in the other object files. Okay, extern symbols mean extern symbols are referenced in this object file but might be defined in some other object file. And local symbols mean these are defined in the current object file and referenced in the current object file, but they cannot be referenced by the other object files. Okay, so global will be your normal global variables, extern will be extern, and local will be your static functions and static variables. Okay, now the way symbol resolution happens, the goal of symbol resolution is to associate every reference of a symbol with one definition, right? So if I have a reference to foo, I need to figure out which definition this corresponds to, right? So let's say I have this program, right, where I have int var defined, there is something extern foo, there is main, which is calling foo, and then there is printf, and in the other file I have extern int var, I have static int var2, and then I'm referencing that, right? So the var is a global symbol because it can be externed into something else in some other object files. Foo is an external symbol. Similarly, if you look at it from the context of the second object file, var is an external symbol. var2 is a local symbol because it's a static and it cannot be referenced somewhere else. Okay. And as I already mentioned, linker doesn't care about variables on stack because they are kind of allocated at runtime when the stack is allocated, and their references are relative to stack pointer, and they are always private to that function. Okay, so essentially what linker's job is, whenever it sees a reference to var2, now since it's var2 is a static variable, it's very easy, right? Because we can say that this var2 must correspond to this var2 only, because var2 is a static variable and it must reference this, right? We need to figure out what does this var correspond to, and when we compiled this file, we didn't know where it points to, right? So compiler would resolve this reference at compile time itself, the var2 reference, because compiler knows that var2 corresponds to this var2, but it doesn't know what var corresponds to. Similarly, compiler doesn't know what foo corresponds to and what this printf corresponds to, right? This is where linker will come into picture. So what linker would do is, this is how the logical structure would look like when the object file is created. So let's say when this object file is created, your text section is 0 to 100, okay? And your data section, since it has only one variable, is of 4 bytes. So it started at 100 and ended up at 104, okay? In context of the other file that we had, let's say the text section started at 0, ended at 50, and the data section started at 50, ended at 54. Right? And we already concluded that compiler is in all position to resolve what is var2, right? Because compiler knows this var2 is always referring to this var2. So in the text section, there will be a reference to var2 saying that this code refers to var2, but compiler doesn't know what this var is referring to, what this foo is referring to, and what this printf is referring to. Okay. So logically, what would happen once you link these two codes together is, logically you will end up forming a code like this, right? But remember, obviously, the linking is happening not at the source level, but at the object file level when the code is already translated. But this is just for the illustration purpose, that after linking, logically, this is what the code would look like. That you have int var, you have static int var2, you have definition of foo, and you have main, which is calling foo. And there are no external references except for printf. Printf gets resolved in a separate way through dynamic linking, which we will see later. So in the link code, this is how things would look, right? You have text section, which is coming from the first object file. You have text section that is coming from the second object file. And remember, I had told you that all these text sections are merged together later by the linker to form text segment. And all these data sections will be appended one after other to form the data segment. Okay. Now, this is where linker will end up resolving the references. Now that it has done it, it knows what is the address of where. So text section, the first text section was referring to foo. So it ended up resolving that foo is now at address 100. So there is a reference from this text section to foo. This text section was referring to var and var2. And var2 we know came from here. So there is a reference for this to address 150, because remember 150 is where the data section started. And var2 is at 154. So var2's reference got resolved to this. Okay, this is what logically happened. Any questions on this? Okay. Now, when we are resolving symbols, right? There are some interesting cases where strong and weak symbols come into picture, and there are rules on how to go about doing the resolution of them. So the rule one, which linker follows, is multiple strong symbols are not allowed. Okay, so if you have two object files where a same strong symbol is appearing in multiple files, then there is an error. Okay, and linker will give error if you run into this case. Okay, so a strong symbol must be defined only once, otherwise you get linker error. Okay, rule 2 says if you have a strong symbol and multiple weak symbols, okay, so if there is a same symbol for which there is a strong version and there are multiple weak versions, then you always choose a strong version. Okay, and all the references will be updated to choose the to use the strong symbol. Rule 3 says that if there are multiple weak symbols but there is no strong symbol, then linker is free to pick any weak symbol. Okay, and in terms of C language, right, functions and the initialized global variables are treated as strong symbols. Okay, so if you have a function definition, it is treated as a strong, that function symbol is treated as a strong symbol. Similarly, if you have an initialized global variable, that is treated as a strong symbol. But uninitialized global variable, okay, these are treated as weak symbols. Okay, let's look at some cases. Okay, so in this particular case, I have int var is equal to 5. Then extern void foo and main is using this. In the other file, I have int var equal to 10 and void foo. Okay, now foo being a function symbol is a strong symbol. So within these two object files, there is a single definition. So there is no violation of the rule. So we are good. Var, since in both cases is initialized variable, right? This results in var being a strong symbol, and we cannot have two strong symbols. Okay, so this would actually result in a linker error. So when you try to link these two things together, linker will complain saying that you have a duplicate definition of var. Okay. Let's look at this case where I have var, the same program, but I have not initialized it. Okay. Any idea what would happen in this case?
The linker would be able to, I mean, it would randomly pick up one.
Correct. So since both these vars are weak symbols, linker is free to choose any one and be done with it, right? It will not complain that you have multiple definitions of var. Okay, although technically if you look at the program, that's what it is, but linker will not complain, and you will get a successful link where one of the var was picked up. Okay, now this was a simple code. If I had something like int versus double or some type mismatch and those kind of things, we already saw linker won't detect it, and you don't even know which copy it will pick. Okay, so linker may pick any copy of any data type, and you can imagine what kind of consequences it can have, right? Depending on linker's decision, your program's output may change or your program may behave differently.
Hello, sir.
Yes.
So if one of the var is weak and another one is strong, so which one linker?
So correct. So the rule 2 will apply in that case, where if you have a strong symbol and multiple weak, the strong symbol will be chosen and all the references will be changed to the strong symbol.
Okay, thank you.
And I do have an example of that. So in this case, I have slightly nasty code where I have an initialized var, which means that this var is a strong symbol, right? And it's a long, so which means this var is 8 bytes. Okay. Then I have int var3, which is uninitialized. So this is a weak symbol. So when these two things are linked together, linker will actually choose this var, which is of 8 bytes. Okay. And it will not choose this one. And then when you call foo and when you write to var of 2, you might end up accidentally writing A and modifying A. Is this clear? Because what is happening is, what linker is saying that, okay, this is strong, this is weak, let me choose strong. And it chose strong. That means it allocated var of only 8 bytes. Okay. Whereas here I am writing to var of 2, which is going beyond that. So I ended up accidentally overwriting subsequent data, which happens to be A in this particular case. So if you actually link this program together, you will see that A is 300 and not 5. So as you can see, these kind of issues can lead to surprising behavior. So you have to be very careful in terms of, which is why you must have read somewhere and so on that you should always initialize your global variables. That's not because that the global variables, if you leave it uninitialized, it is problematic, because uninitialized global variables are still 0. But if you don't initialize your global variables, it also means they may get overridden by some other strong definition of that symbol. Okay, because this uninitialized definition of var got overwritten by another definition of var, which was strong. So uninitialized global variables lead to these kind of problems, which is why, first of all, you should avoid global variables if possible. If they are must have, then at least initialize them. So you know that this is the exact definition that will be picked up. And if someone tries to do a conflicting definition by initializing it, you'll get an error. That's better than silently having some weird behavior of your program. Any questions so far before we move on?
Sir, you just said that uninitialized global variables are 0, but aren't they containing the garbage values?
Uninitialized global variables are 0. Uninitialized variables on stack are garbage.
Okay. Thank you.
I just wanted to confirm if the different data types does not matter to the linker, because if long
Correct.
var is also uninitialized in this case, then it would just pick up any one of those.
Correct. So if I had not initialized this var, then linker may have chosen this one or this one, you don't know. If you, in fact, it would change based on the linking order. Like if I do G++ A dot O followed by B dot O, I will get one behavior. If I do G++ B dot O, A dot O, I'll get a different behavior. Because in most common implementations within the linker, they will choose the first definition. Moving on, let's look at the relocation, which is somewhat complicated topic. But essentially, what we saw just before this quiz was we kind of merged all the text sections together and all the data sections together and so on. So the offsets of the variables were changed, right? So that needs to be somehow handled, and we need a way to update all the references. So for example, let's say var was originally at offset 100, and after merging that happened at linker stage, it became 200. We need some way to make all the references to point to 200, right? So when linker is merging these things together, as I said, it will form these code segment, data segment, and so on. So what it is essentially doing is it is changing the offsets of the variables. Like within the data segment, the offsets of variable that belonged in this dot data section would have changed. Similarly, what it would have changed here and so on. Okay. So what is relocation? Okay. So relocation is essentially after you do this, all the addresses that you have will be final. Okay. But before this, they are all modifiable, which is why the object files that are produced by the compiler are called as relocatable object files, because they can be relocated further by the linker. But once linking is performed, they become executable files because you won't change them beyond that. Okay. So compiler generated code will have references and they cannot be final. So for example, when I'm seeing the compiler generated code where I had a call to foo, there is no way the address of foo was known, right? So the compiler cannot generate address of foo. So it essentially will fill out something there, which we will see. And that will need to be modified because it will eventually need to be modified by actual address of foo, right? So what compiler essentially does is when it generates code and it doesn't know the address, it just puts some data at that position, and then it generates something called as a relocation to indicate that this particular reference needs to be changed, and I don't know the object of that. And there are relocations on x86, and we'll see an example of these. So there is something called as R386 PC32 and R38632, which I'll demonstrate with an example. So what relocation R386 PC32 does is it relocates the reference pointed by this relocation with the 32-bit relative PC relative address. Okay, PC relative, in case anyone doesn't know, PC relative essentially means address that is relative to the current instruction. So if I am on instruction 1, right, and I need to go to third instruction, then what is the offset from the first instruction to the third instruction would be the PC relative address. Okay, it is not to the beginning of the section. Okay, and R38632 is simple. It's the actual address in the memory. Okay, you might be wondering what these names are and who will define them. So there is a contract known as Application Binary Interface, or ABI, which essentially documents all these relocations and things like that. Okay, so let's see this with an example. So let's say I had an object file where main is calling foo, okay, and foo is extern. Okay, now what will compiler generate as a code, right? Because compiler has to generate a call instruction. The call instruction in the x86 assembly, you would see that it takes a address as an operand, where the address that you give must be the address where you want to call. Now, there is no information available to the compiler. So compiler will simply say that, okay, call address 0. I don't know what is 0, but compiler also generates the relocation saying that, you know what, this 0 is not really 0. It needs to be changed with address of foo. And the way it needs to be changed is by applying this relocation called as R386 PC32. Okay. And there is this other object file which actually has a definition of foo. Okay. Now what linker does? So linker will take these two object files together. Okay. Linker will merge the text sections to form a text segment, right? So linker will take this text section, linker will take this text section, will append them together to form this text section. Okay. But Now what will happen is when that process happens, then linker actually knows what is address of foo, right? Because it created that layout of the text section. So let's say foo happens to be at address 100 after that layout. Then linker can actually go and fill this call with call to foo, which will be essentially call to 100. Okay, if foo happens to be 100. Any questions so far? I'll get into details of the relocation, but conceptually, is there any question on how this process is working? Okay. So now let's look at more concrete things in terms of ELF, what will be there.
Just to confirm, the linker will like actually physically copy the data into a new file to make the text sections. It will be like a disk copy.
So the way linker would work is it would essentially do all these merges at in-memory data structures. It will not be writing to a disk at this stage, but finally whatever in-memory it has created, that will be written out to the disk. So it's not that linker is copying this text section, writing it to file, writing it to a disk file, then taking the next object file, appending that to the disk file. It's not going to do that. That is going to be very inefficient and that is one way to implement linking, I would say. I won't say it is not the correct thing, but that's not how typically linkers would do. So the way linkers would do is essentially they would read all of this data that came from the input files into some in-memory data structures where all of this information is represented in some structures which are easy to manipulate, easy to append to, and so on. Then linker will actually create a layout which it can then write to a disk file. Because you would want to not do this disk operations as much as what would happen during the linking.
Right, thank you.
One more question. So the addresses that we're talking about here are all virtual addresses?
Yes.
But, okay, so essentially what you're saying is that I think I understood the final when it says call foo, because the address is not known to the process before it starts executing.
It is known in a sense that this again could vary from platform to platform, but I would say in the most common platforms like Linux, Windows, etc., the address space layout of a process is fixed by the ABI. So the ABI of that particular OS and processor would state that the process address space would look like this, where the text sections must start at some address, which in fact I will show you in subsequent slides. So that is always fixed. So the virtual addresses where the text section starts is usually fixed on most of the common processors. There are a few things where they do change stack addresses and so on for avoiding security issues, but that is for more advanced stuff. But in most common cases, the address space layout of a process is fixed, and that's same across all the processes.
Wait, so you're saying that the starting address is fixed or the offset is fixed?
Starting address is also fixed. The exact memory location where _start is loaded is fixed.
So we rely on the MMU to handle all the translation to the physical memory. We don't care about. Okay.
Yes,
Which
is in fact one of the benefits of virtual memory. If you were relying on world when there was no virtual memory, so if you actually study old linkers which were dealing with systems that didn't support virtual memory, then yes, the linker, the addresses that linker lays out will be more like offsets, and loader will actually allocate offsets based on where in the memory things are actually available. And every time you load program, it may get loaded at different address. But with invention of virtual memory, we get all this interesting stuff that you can make assumptions which otherwise wouldn't be true because you have this indirection that was created. So every process can load _start at a fixed address. Physically, it might be at a different location, but that would happen automatically when the page tables are set up.
Yeah. And we assume that the security and all the fencing between processes is handled by the MMU itself. MU and the
So you
processor.
can't, yeah, so you can't transfer virtual address from one process to other process easily without doing explicit sharing and so on. So yeah, by default, if you say address 100 in process P1, virtual address 100 and virtual address 100 in process P2, they might be referring to two different entire things, right? So you can't simply take a pointer from one process, pass it as a value
Yeah.
to other process and expect it to work.
Absolutely.
Unless you do some explicit IPC or you have set up your pages that way.
Sure. Yep.
Okay.
Thank you.
So let's look at somewhat more concretely what we just saw in earlier diagram. So we have this int main which is calling foo, and foo is extern, right? Now we know that there is a text section that will contain some stuff, right, which is code for main. There is a new section that will be present which is called as relocation section, which in this particular case is .rel.text. Okay, so what this is saying is there is a relocation on the text section. So that means the text section needs to be modified in some way by the linker. Okay, and the information that you can see associated with the relocation is something like there is an offset, which in this case is 7. There is something called as info, which is 902 hexadecimal. There is this type, which I already mentioned is R386PC32. There is something called a sim value, and there is a symbol. Okay, so symbol is foo. What in conceptual terms, what this relocation record is trying to say is at offset 7, we need to change the value at offset 7 by foo using the computation that is described by R386PC32. Okay, so if you actually look at the disassembly, you would see that at offset 7. Okay, so if you actually look at the offsets, you will see that at offset 6 there is a call instruction. The call instruction, if you read the x86 manual, you will know that it is encoded as E8 followed by 4 bytes, which gives the actual address which needs to be called. And remember, this call is a relative call. So the way x86 call works is it is relative to the current instruction. So if I have to call any function, I need to give address of that function relative to the current instruction. Okay, I'm not giving the exact address of foo, I'm giving the address of foo relative to the current instruction. Okay. So what this relocation is saying is we need to change value at offset 7, which is essentially this value, right? Which happens to be -4. Okay. Like if you interpret this value, it is actually -4, 2's complement. Symbol is foo, so we are changing that with address of foo, and the type of the relocation is R386PC32. Okay, now the computation that linker would do is something like this. Linker will take whatever is the address of foo. Okay, it would add the addend. Addend in this case is this value which was -4. Okay, and it would subtract the offset. Okay, because R386 PC32, this PC32 means relative to the current instruction. So what it is doing is that it is actually taking address of foo and subtracting the current instruction address. Okay, so after applying relocation, it would essentially become this. Okay, so essentially, let's say the piece address of foo was something like this, 0x8432EF, right? Then you add -4 to it because you want to get to this bytes, and then you subtract the current instruction address. Note that these are the final memory address, final virtual addresses in memory. And this would essentially translate to this, which is 80483E84. And if you actually look at it, that would be the address corresponding to foo. Okay, so what we essentially did was we modified the operand of call instruction with address of foo using a relocation. And that's how an undefined reference which was present in main to calling foo was actually modified by the linker to actually point to foo. Any questions here?
I have one question, but it is not related to this. It is it is a very difficult question.
Okay, go ahead.
How do you define dynamic binary translation in this?
How do you, as in? I didn't get that.
So when you implement virtualization, you implement something as known as a dynamic binary translation, right?
Yes.
Yeah. So how would that be implemented in case of a fixed address space?
So what would essentially happen in such a case is, see, typically when you have VMs, you are still expected to run the same binary, right? So your binary is already present and you're simply running that application. Instead of on native OS, you're probably running it on your VM, right? So you're not, so this binary which was produced after linking is what will be seen by the VM, right? And when you implement that VM, you know what was the contract followed by this binary, because you need to know what was the ABI followed by this binary. The ABI for that particular binary would have stated that the program gets loaded at this particular address point, and I'll also show you where it is documented or where it is captured in ELF. So you actually know what is the code assumption, and then you will have to actually work with that. So the way dynamic binary translation would actually handle it is, in fact, it has to do much more, because what would happen is when this binary is fed to the VM, it would essentially need to interpret each of the opcode, because it potentially need to translate it into the equivalent opcode that the VM is supporting. So it actually has to interpret much more than what linker was doing. Right? Because in linker's case, linker was actually agnostic. So if you look at all of this computation which I showed, linker actually didn't know that this was a call instruction, right? Linker didn't have to interpret that this was a call instruction, so I have to do it in this way. It was this relocation which simply gave some mathematical formula which linker needs to blindly apply everywhere this is used. So linker didn't interpret the context, and it simply applied it. VM, on the other hand, will probably need to even understand the context. So it knows that we are dealing with a call instruction and it can handle it. Because VM anyway needs to translate this call into an equivalent call on that target OS or target machine.
Yes.
Does that
Yeah.
make sense?
Yeah. Thank you.